All right, in this lesson, we're going to review the rules for the derivatives of an inverse function. So first, let's review what an inverse function is. An inverse function will take a function, and it will reverse the input and the output operations of that function. So basically undoes the original function. Okay, so we denote an inverse function with this f negative 1. Just read it as the inverse of f. And a function has an inverse if it satisfies this for all domain values. That when you take the function, the original function, and you put it inside the inverse, you compose it, that is going to equal x. And when you compose the inverse, when you put the inverse inside of the original function, you also get x. All right? So this is just showing that one of them undoes the other. X goes into the inverse, and that goes into the original, and x comes out. X goes into the function, and what comes out of there goes into the inverse, and x gets spit back out. All right? So they're undoing. That's what that notation is showing there. So we've got some examples of inverse functions, adding and subtracting our inverses. X cubed and the cube root of x are inverses. E to the x and natural log are good inverses. And then we have our trig inverses. So we have the sine of x and what we call the arc sine, also known as the inverse sine. Okay, so here an angle goes in and the sine value comes out. Here we put in a sine value and this spits out the angle. Okay, all right. Well, remember that not all functions have inverses. That's key. Okay, so it's got to pass the horizontal line test in order to have an inverse, or more accurately we call this a one-to-one function, which means for every x, there is only one y. And for every y, there is only one x. So it's got to go both ways. Okay? That's what one-to-one means. All right. Well, before we look at that rule there, let's come over here and let's take a look at a Desmos here to give us an idea of what's going on. Look at this graphically. All right. So we're going to look at a function here. So we need a function. It needs to be an invertible function. So we could pick any function, but let's pick x cubed. That's a nice function. Now notice this is invertible because it passes the horizontal line test and the vertical line test. So it's a function and it's an invertible function. Okay. Important note is that all invertible functions have to be always increasing or always decreasing. It's what we call monotonic. So that means it's always increasing for all x on negative infinity to infinity, or decreasing for all x from negative infinity to infinity. So it's always increasing or always decreasing. Keep that note in mind. That's always true for invertible functions. All right. So we got x cubed. Well, if we inverse this, the inverse of x cubed is the cube root of x. So there, the blue function is our inverse function. And so this g of x is our original function. All right. So here's the story. We want to consider the derivative here. So we need a point on this. So we're going to find the point a g of a. All right. And a is just going to be a slider, as you can see here. All right. So right now a is at 1.5, which is the slider right here. So there's the point a g of a. All right. Now, since this is the inverse, remember an inverse flips the x and y coordinate around. So the point on here will be g of a comma a. Notice they're reversed, right? All right, so we're going to reverse that. There it is. So here's the point g of a comma a. Okay, now we're going to call this function f. All right, so these are inverses of each other, right? Okay. And we can move these points around, all right? And a g of a, wherever they go, a g of a is on the red one, g of a comma a is on the blue one. All right. Now, let's think about this, all right? Suppose we want to find the derivative of this red line, and we're not very familiar with it, but we are familiar with the derivative of the blue one. All right, so we can look at this. Let's find the derivative. Let's find a tangent line, because we know the derivative is the slope of the tangent line, right? So here we have the point a comma g of a. So we're going to find the tangent line going through there. So we'll use point slope form. Y minus g of a, the y value, equals g prime, that's the derivative here, times x minus a. All right, so let's get our derivative going here. And there it is. So there's our tangent line on g, the red function. And let's get a tangent line on the blue line. This is the point g of a comma a. And we want the tangent to f, because this blue function is f. All right, so here's our point slope form for that. Let's get it showing. Come on. There we go. All right. And so as we move this here, these two lines are tangent to their respective functions. All right. When we come down here to the point that they have in common, this is the point 1, 1. And so you can see the slopes of the two lines here. All right. They're tangent, again, to the red and the blue. Now, what are the slopes? Let's think about that for a second. All right, I think we can actually count it here. Notice on the red, it goes through this point 1, 1, and it also goes through the point 2, comma 4 there, right? Is that right? Yes, that is right. So we can see that. Okay, so it's going as a slope of, right there at this moment in time, its slope is 3 over 1. The blue line here has a slope of up 1 over 3. So the slope here is 1/3. Now let's see if that is reasonable. What's going on? Well, they're inverses of each other, right? Well, slope is rise over run, which is y's over x's, y2 minus y1 over x2 minus x1. Does it make sense that the slopes would be reversed? Well, these are inverses. What happens when we have an inverse function? Well, the x and the y switch places, right? So there's kind of some simple convincing evidence that yes, the slope of these two lines should be inverses of each other. And we won't go into a big proof on that right now, but they are. So the slopes are inverses of each other here. And so that's useful, all right? Well, now we need to get an expression for it, okay? So the slope here, let's say that we know the slope of f. All right, so the slope here of this function is f prime at g of a. Okay, so again, g of a is the x-coordinate because this is flipped from g. So this is f prime at g of a. Well, if that's the case, then this slope here, the red slope, let's get red going on here. There we go. The red slope is going to be 1 over the derivative of f at g of a. Okay. Again, we're plugging the old y value because the y value of g is the x value of f. Say that again. The y value of the g point, g of a, is the x value or the input for f. Okay? That's why we're putting g into f there. Okay? So there we go. Okay? Once again, so the slope of this is f prime. Okay? And so this is the inverse of that. All right. Well, let me rewrite this. The slope of the red line is just g prime of a. And there we can see our important formula. This is our formula that we're going to want for the definition of the derivative of an invertible function. Okay, so what is this saying? The derivative of a function g is 1 over the derivative of the inverse function f at g of a. So if we don't know how to find the derivative of g but we do know how to find the derivative of f, we can use f, the inverse function, to get the derivative of g. And that's our function there. All right? So there's our rule. Okay, and we'll put an x instead of a g. So here we have it. If f of x and g of x are inverses, okay, we know that f negative 1 is equal to g of x. So we can say this rule right here, and this is one to remember, one to memorize. Okay, the derivative of g is equal to 1 over the derivative of f of g of x. All right, and so this is really nice and really useful when we don't know how to find the derivative of g, but we do know how to find the derivative of f. All right, well, let's see how we can use this here on some practice AP questions here. So in this question here, we know that f and g are inverses of each other. So there's kind of that tells us several things here, all right? So since they're inverses, that means they're invertible, which means that they are monotonic functions. It means that they are increasing or decreasing for all real numbers, okay? So they are increasing for all x or decreasing for all x, one or the other, all right? So that's going to be important. All right. And we're also told that it's differentiable. That's important because we're going to use our rule here. And we're told that f of 3 equals negative 2. Now, whenever we're having an inverse function here, it's useful to write down this fact. If f of 3 is negative 2, then g of negative 2 is 3 because they're inverses. All right. Now, we're talking about the derivative. We're told the derivative of g here. And so we know the derivative of g, so we can use that. What we don't know is we don't know the derivative of f. So we're going to write our rule here. The derivative of f is the reciprocal, or 1 over, the derivative of g composed with f of x. Again, we're putting the y value, the f of x value, into the derivative of g. Well, the question here is, which of these following statements are false? Well, we can glance at these. Notice they're all about f prime. We got 3 numbers here. And I'm going to kind of ignore those for a moment. And I'm going to look over here to figure out what we can actually do. So which x value do I actually know anything about? Well, I know something about f of 3. So I know something, I can put 3 in here. So let's go ahead and do that. And again, when you're doing these things, when you're using these formulas on these kind of tricky problems, it's a really good idea to take a moment to write it out like this, because then you can see it and avoid silly mistakes. By seeing it, you can say, well, I don't know much about this. I hope I missed an apostrophe, a prime there. It's f prime of 3. I don't know what f prime of 3 is. Wasn't told that. But I do know some of this. I do know what f of 3 is. f of 3 is negative 2. So I can rewrite this. This is 1 over the derivative of g evaluated at negative 2, because f of 3 is negative 2. Well, do we know the derivative of g at negative 2? We sure do. It is negative 4. So this is 1 over negative 4, also known as negative 1/4. So we know that this number 2 here is true. All right, now the question asks us which one must be false. Now here's where this question gets pretty tricky. It's tricky here because this tells us that the derivative at 3 is negative. So whatever this graph looks like, we don't exactly know what this graph of this function looks like, but it has to be going down. It's got to be decreasing down to the right. It's monotonic, so it can't turn around. The moment it turns around, the moment we have some function that's going down and it turns around or something like that, this is not invertible. It doesn't pass the horizontal line test. So it has to be always going down. So it's monotonic, always going down, something like that. All right? So that means that this is not possible. So our answer is that I must be false, because that is a positive slope, which means it's increasing. Now, we don't know that this is true. We don't know that f of negative 5 is negative 4, or f of positive 5, I should say. We don't know that. But we do know that it has to be negative. So we know that there is no way that f of 0 could be 1/4, because that's increasing. It can't turn around. All right? So there are some things to think about there for inverse functions. And again, you want to get really comfortable with this definition, this rule right here. All right? Thanks a lot. Good job.